Hey everyone, and welcome to this explainer. Today, we're going to peel back the sheet metal. When we look at a modern electric vehicle, it is incredibly easy to just get distracted by that sleek exterior, the massive touchscreens, or that really fun instant torque. But to truly appreciate what's happening out on the road today, we need to look way past the surface. We need to understand the deeply complex ecosystem of systems working together in perfect harmony right beneath the chassis. It's a fascinating question, isn't it? What actually makes a modern EV tick? Think about it. How does a single vehicle manage to flawlessly balance raw, high-voltage power delivery, advanced central computing, and near-instantaneous hazard perception, all while barreling down a highway at 70 miles per hour? It's honestly not just a car anymore. It's a highly advanced robot. Okay, let's dive into this. To make sense of all this engineering, we're going to map out the EV's anatomy almost like a biological system. First, we'll look at the brawn, which is the efficient power. Next, the brain, or the vehicle control unit. Then the senses, which covers ADAS perception. We'll see how it all comes together in sensor fusion and action, and finally, we'll take a peek at the future of mobility. All right, starting right off with part one, the brawn, efficient power. Let's look at a foundational example from Renaissance, their 500-watt onboard battery charger, which is specifically designed for the absolutely booming two-wheeler EV market. Now, this 500-watt platform is a total game changer. Why? Because it eliminates the need for highly specialized, expensive charging infrastructure. Instead, it allows these vehicles to just ingest power directly from a standard AC outlet. You're basically plugging in a vehicle with the exact same ease as your laptop or your coffee maker. It's all about unparalleled user convenience and raw utility. But you might be wondering, how does it do this without just wasting a ton of energy? Well, the secret lies in the materials. This platform utilizes 650-volt gallium nitride, or GaN, FETs. Compared to traditional silicon, GaN technology delivers absolutely exceptional efficiency. In the real world, what this translates to is significantly faster charging and, crucially, far less energy wasted as heat. It creates a highly reliable, incredibly dense power stage. If we dig just one layer deeper, this charger architecture actually includes two highly advanced internal power stages. First up, you have a power factor correction, or PFC stage, which makes sure that AC to DC conversion is smooth and efficient. Then an LLC resonant converter stage steps in, delivering over 95% peak efficiency for the DC to DC conversion. But here's the cool part. It's not just dumb power. There's an integrated microcontroller unit that reports critical data, like battery health, directly to the vehicle via the CAN bus. And the CAN bus is basically the car's internal central nervous system, so it's really intelligent brawn. Moving right along to part two, we've got the brawn. Now let's talk about the brain, the vehicle control unit. To really understand this brain, we have to talk about a massive paradigm shift in the industry, the software-defined vehicle, or SDV. An SDV is a vehicle where the core features, the functions, and even the driving dynamics are enabled and governed primarily by software. The vehicle control unit, the VCU, is the physical brain that facilitates this modern, service-oriented architecture. It acts as the central computer and the main gateway for the entire car. This perfectly illustrates exactly what makes a modern VCU tech. It's a multi-core powerhouse. It's also heavily regulated, complying with strict ASIL functional safety standards, which basically means it meets the absolute highest automotive safety integrity levels required to keep you alive. But the real magic here is its ability to perform no-wait over-the-air updates. By leveraging an onboard embedded multimedia card for massive data storage, the VCU can download and prep huge software upgrades seamlessly in the background. It keeps the car constantly updated without ever subjecting you, the driver, to frustrating vehicle downtime. Okay, on to part three. This senses, specifically ADAS perception. Take a look at how these specific sensor zones are mapped out around the vehicle. We aren't just looking straight forward anymore, right? Multiple, highly specialized sensor technologies are working perfectly together to create a 360-degree protective bubble around the car. You've got long-range radar for your adaptive cruise control, medium range for checking your blind spots, ultrasonic for parking, and high-def cameras keeping an eye on lane departure. Now, two of the absolute most critical senses here are radar and LiDAR. And honestly, they do very different things. A 77 gigahertz millimeter wave radar is fantastic at detecting long-range radio velocity. It can calculate the exact speed of a car 200 meters ahead of you. But it kind of lacks fine structural detail. That's exactly where LiDAR comes in. Using 905 nanometer pulsed lasers, LiDAR gives you stunning, centimeter-accurate 3D mapping of the environment, usually in a 60-degree frontal arc. You absolutely need both of these strengths to handle different driving and weather conditions. But here's the catch. Integrating all these senses is kind of an electrical nightmare. Look at these distinct voltage requirements. You have a 77 gigahertz radar running on a standard 12-volt rail, sitting literally right next to LiDAR lasers that demand massive 100 to 400 volt pulses. Meanwhile, your high-definition CMOS cameras rely on these incredibly sensitive, tiny 1.8 volt to 3.3 volt logic supplies. It is a wildly diverse, complex electrical environment, and it all has to share the same underlying architecture. Which brings us to part 4, sensor fusion in action. This is where it all comes together. Now, what's really interesting here is the red block right in the center of this ADAS ECU diagram, the power supply. See, an EV is an inherently noisy electromagnetic environment. It is just full of switching inverters and massive power draws. If that electrical noise bleeds into those highly sensitive 1.8 volt camera rails or the radar receiver, the car basically goes blind. So that red power supply block is the literal shield protecting the vehicle's perception. To pull this off, engineers use something called soft switching converters. Let's break down the jargon for a second. This is a highly specialized power design that smooths out the electricity, reducing the ripple on the output line to a minuscule 14 millivolts. By delivering power that is this clean and stable, it directly prevents the radar and LiDAR from being blinded by electrical interference. It vastly improves their signal-to-noise ratio. So, with clean data finally secured, the brain goes to work in this relentless 10-millisecond control loop. Step 1 is perception. Every radar pulse, LiDAR time of flight, and camera frame is simultaneously sampled and buffered. Step 2 is fusion and decision. An algorithm called an extended Kalman filter actually fuses all these separate object lists into one unified worldview, instantly prioritizing immediate safety hazards. Step 3 is actuation. Commands are dispatched in real time over the CAN bus to the brakes and steering. This entire 3-step cycle happens 100 times every single second. To put that into perspective, it takes you about 300 milliseconds just to blink your eyes. In that exact same time, the car has evaluated the road 30 times. And the results of this biological-like reflex are just staggering. In extensive field tests measuring forward collision warnings, this sensor fusion directly resulted in drivers responding to hazards 0.4 seconds faster. Now that might sound small, but at highway speeds, that fraction of a second reduces peak closing speeds by 12 kilometers per hour. That is quite literally the difference between a minor close call and a catastrophic rear-end collision. All right, let's wrap things up with part 5, the future of mobility. Everything we've talked about so far is basically the baseline for current level 2 tech. It prevents collision, sure, but it still requires your constant supervision. So what's the next step? Scaling this architecture to level 3 autonomy and beyond means the car takes full responsibility in certain conditions. To actually do that safely, the hardware requires complete fail operational redundancy, meaning if one power supply or sensor array fails, a backup instantly takes over. It also requires advanced vehicle-to-everything, or V2X communication. This allows cars to cooperatively perceive hazards miles down the road just by talking to each other. We are laying some incredibly complex groundwork today for a pretty radical tomorrow, which leaves us with one final profound question. What happens to the driving experience when level 4 and 5 autonomy finally transform the driver into just another passenger? When the brain, and the senses of the machine are so perfect, we simply let go of the wheel. It's a fascinating future to look forward to, for sure. Thanks so much for joining me on this explainer, and keep your eyes on the road ahead.